Alright, yesterday we focused upon using the net change theorem to identify a function by looking at how the function is changing in terms of physics. Now to do this, we referenced a chart that's really helpful for a lot of this section. So I want to make sure you put that in here again, just to make sure it's really nailed home before we look at our next problem. And we'll continue these themes as we go forward. Let's see. That chart indicates that in physics there are four primary functions of motion. There's the position function, the velocity function, the acceleration function, and the jerk function. And the thing is, because of calculus, all of these things now become related. You can take derivatives to move down this list. So to go from position to velocity, derivative. From velocity to acceleration, another derivative. From acceleration to jerk, another derivative. To work backwards on this list, we have to integrate. Again, that's a reference to the second fundamental theorem of calculus, is that this allows us to take this function and go backwards. So if I want to determine the acceleration, I can use a jerk function and integrate it. If I want to determine the velocity, I can use the acceleration function and integrate it. If you're in position, you integrate. Obviously, if I had a position function, I wouldn't integrate to find the position. I just plug in the position function. This is only really useful if I have the quote-unquote wrong equation. I have the velocity, but I want position. I have acceleration, but I want velocity. It's only useful if I have the wrong equation. It'll allow me to find that missing piece and then work backwards to solve. Now, as I mentioned last time, the not so subtle threat that every single year a position function question is every single year on the test. It's not just on the test for AP. It's also on mine. Sometimes two. Because this one's one of those that always pops out. It's always important to know you have to have this idea down with it's firm.
Sometimes two tests or two problems?
Two problems on my test. Like one on the in class and one on the other class. It's a good time. So let's do another example using this information. So this time, same properties as yesterday. We were told the velocity function in feet per second is given for a particle moving along a straight line. Find the displacement and find the total distance the particle travels over the given interval. As a secondary reminder from yesterday, our two terminologies, displacement versus distance. Displacement is found by the standard integral. Whereas distance, the total distance traveled, is determined by looking at the absolute value. So for each of these pieces, it's necessary to be able to do both functions. Well, let's try it out. This time my function, a little bit tougher. We're looking at the function, yeah, let's do a trig one. Yeah. So, v of t is equal to cosine of t plus 2t. In this case, our bounds are set by 0 and 3 pi. So, the cosine function is going to cause this thing to oscillate back and forth between 1 and negative 1. The 2t is going to cause it to continually go upwards in value. So it's going to cause this thing to oscillate velocities, but going upwards over time. Well, let's talk about distance and displacement. To find the displacement, we take this function, we integrate this function from 0 to 3 pi of cosine of t plus 2t. With respect to t. Alright, let's do it. Integrate the function. What is the integral of cosine of t? Sine of t. Remember, sine becomes cosine, so then cosine has to become sine. And the integral of 2t? Squared. Next thing we do, plug it in. If I plug in 3 pi, you plug in 0, and determine what happens. So displacement would be 3 pi plugged into the sine plus 3 pi squared minus 0 plugged in. Those same two pieces. Sine of 0 plus 0 squared. Alright? Let's do these one first. Sine of 0, of course 0. 0 squared, 0. So this right hand side is just 0. Pretty common. Left hand side. Sine of 3 pi. Ooh, that should begin to circle down. Sine of 3 pi. 0. It's also 0. And then 3 pi squared.
9 pi squared.
9 pi squared. Which is, what, 82.7? Somewhere in there. For now, let's just leave it right there. That's a good number. Question so far. We've determined the displacement, how far it has moved from the beginning to where it finishes, not the overall distance, just the displacement. What's the major change that turns us into a distance problem? Absolute value. We did this exact same problem, but now instead of doing it with just the integral, we're going from 0 to 3 pi, the absolute value of cosine of t plus 2t dt. Okay, with an absolute value function, what's the very first thing we need to do? Determine where those zeros are going to be. Figure out what's going to happen in this function when it's going to split apart. Boundary points or split points. So, when will cosine of t plus 2t equal 0? At 0? No. If I plug in 0, cosine of t, or cosine of 0 is 1, plus 2 times 0 would be 0, 1 plus 0 would be 1. Delicious. Where does cosine of t plus 2t equal 0? Michael, I love where you're going with this.
I was going to go look it up on Desmos.
Yeah, we got to find our piece, right? This is not one that we would expect to solve by hand. So, let's put a graphing calculator. Let's find some other technique we could try. We need to figure out a solution for this. Let's see what this happens. Now, make sure we're looking for solutions particularly between 0 and 3 pi. So I'm going to pull up Desmos and see what happens. Now, I can do this a couple different ways. The most common way is just to plug this in and look for x-intercepts. Alternatively, you could also set them equal to each other and kind of work backwards. Both work well. But you need to be able to find a solution. So, let's plug them in. We have cosine of t. So cosine of x plus 2x. Doesn't.
Imaginary.
Happens in imaginaries. This one does not actually have an x-intercept in that range. So, where is this going to split apart? It doesn't split apart. This function does not split apart. So the question becomes, what happens to those absolute value symbols? Do they stay? Do they become just parentheses? Do they become negative? In this case, this result is always positive. So it never has that crossover point. This kind of function, in order to determine what its actual value is, we can just deal with this one. This is the only function we've seen so far whose distance and displacement are the exact same.
9 pi squared.
So 9 pi squared is actually the solution for both of these. That is possible. They're just going in a straight path. Makes no stops or turnarounds. Distance and displacement can totally be the same. It's rare in these kinds of problems, but it does happen. So look for them. be confident that if you find that solution, you're just like, okay, these are the same. We must be doing it right. The alternative is we question which steps we took and see if we made mistakes in them. I think in all of your homework problems there are boundary points, but I want you to see at least one where it doesn't have a changeover. These have the same values. And that suggestion to go to Desmos or to Wolfram, fantastic. Okay, use your graphic calculator. Find that functional value if there is one. If you find you can't find it by hand, or have difficulty find it by hand, calculator is your friend. Okay, try by hand first, but if you run out of options, choose your options. Okay. Any other questions on net change rules? Specifically with their particle motion problems. We need to see the other one. Do we want to see some examples from homework? We have some time left today.
Another one of the word problems.
Mhm.
One job, struggling with word problems.
One of the word problems.
Is it posted?
I don't know. Is it?
Has four form been posted yet?
Thought I posted it. If I haven't, I guess I should post it.
No, you don't have to.
Oh.
You don't have to post it.
It's probably a good idea. Alright, so 49. Limit as n approaches infinity of the following function. Summation I equals 1 to n of 24i over n squared. Looking good so far? Okay, I want to remind you, before we do any of this, the limit as n approaches infinity of a number divided by n is 0. That's the key word I'm going to use multiple times. On any of these limit problems, whether it's in section 4.2 or 4.3, if it's a limit problem, this rule plus a bunch of factoring and canceling rules, that's what I'm going to use primarily to solve it. So I'll show how I get to that rule once I go here. To start with, I want to isolate the I as much as possible because that's the part the summation deals with. The n and the 24 are not important, so I'm going to pull those out to the limit. Limit, n approaches infinity, 24 over n squared times the summation I equals 1 to n of I. So since, again, this summation symbol only affects the I, 24 is not an I, so it's not going to be affected. The n squared is not an I, it's not going to be affected. So you can pull it out. So you end up with the summation. Now this summation is one of our theorems. I hate you. One of our theorems. The theorem states that if we have something that is going a summation to n, it is equivalent to limit n approaches infinity, 24 n squared. This is equivalent to n times n plus 1 over 2. What I'm going to do now is I'm going to do a bunch of simplifying and splitting algebraically. Now, for these steps, I like to go a little fast, so if I need to show extra work, you just let me know. 24 and 2 are going to cancel, leaving 12. And are going to cancel, leaving me with the following. Limit n approaches infinity of 12 times n plus 1 over n. And what I'm going to do, I'm going to distribute the 12 and then split this thing into two fractions. So, limit n approaches infinity, the 12, and the n are going to go in one fraction. The 12 times the 1 are going to go in another, with n's in each. There's a single fraction and split it into two fractions. Always allowed as long as the subtraction or addition is in the top. Now at this point, you notice that n's can cancel on the left-hand side. So just 12. On the right-hand side, we have 12 over n, and now I use this property. Anything over n, we assume will go to 0, meaning all that's left behind is 12, our solution. So, a bunch of different components to make that happen. But this is the primary rule we use, along with our theorem. I believe it was theorem 4.3. It allows us to take that function and rewrite it in terms of I and n, getting rid of the summation symbols. We also talked about 53. I'll treat 53 the same way. 53. 53 states limit n approaches infinity. Summation from I equals 1 to n. Of 1 plus I over n times 2 over n. As it turns out, this particular function is actually a really common one in section 4.3. This is f of c sub I times delta f, or delta x. So I'm going to follow the same rules I did over there. If it doesn't have an I in it, I want to find a way to move it out. So in this case, the 2n becomes a limit as n approaches infinity of 2 over n times summation I equals 1 to n of 1 plus I over n. You might be saying, well, can I move the 1 out? Well, it's actually attached to the I by an addition sign. The multiplication symbol can be factored out like any other factor can. Addition cannot be just factored out. So now I'm going to split this into multiple summation problems that I can also split apart. So for this piece, this is all being applied inside of the limit. Let's now do limit as n approaches infinity, 2 over n, times. Okay, I want to split it into two pieces. The summation from I equals 1 to n of 1 plus the summation I equals 1 to n. Now, I over n, the I I'm going to keep in because it has to stay in, it's I. But the over n, I'm going to move outside. And this is starting to get nasty. My hand ready. Towards the end of the week, I'm going to try that ready again. Summation I equals 1 to n. I stays inside, the 1 over n moves outside. And so, once again, what I'm going to do, all that stuff is still inside of that limit, so I'm going to take each piece and use the theorem on it. We have a theorem that states that a constant being summed to n is just n. So I write the limit as n approaches infinity. The 2n is still outside, times. Now this piece becomes just n. That's part of our theorem. It states that a constant sum to n is just n. Plus 1 over n. And summation to I is that same formula. N times n plus 1 over 2. Now the rest is just kind of simplify and apply that last rule. So let's do that. So far I've used our theorem twice, once to get this result, once to get that result. The rest has been a bunch of factoring stuff. Now I'm going to distribute that 2 over n to each piece and then start trying to simplify everything that I can. So I distribute 2 over n to here, distribute 2 over n to there, and see what happens. So this becomes limit as n approaches infinity of 2n over n plus 2 over n squared times n plus 1 over 2. I haven't simplified yet because I want to make sure it's very clear that where these pieces comes from. Now I'll simplify. N's cancel. 2's cancel. N's cancel. I'm left with the following. Limit n approaches infinity of 2 plus, on top I have n plus 1, on bottom I have n. Just like before, I'm going to split this apart into two pieces. N over n plus 1 over n, and then simplify each piece. So, take my component, limit as n approaches infinity of 2 plus n over n plus 1 over n. Now, this piece is just 1. Fitted with 2 plus 1, that's 3. Plus 1 over n, this becomes a 0. So that's just 3. All that work to get 3. Now, this problem, let's see. The original problem actually answered the question if f of x was equal to 1 plus x evaluated from 1 to 2, I believe. I have to double check, but if you actually did that problem as an integral, you should get the same solution, which is kind of neat.
That's 53.
Yes, 53.
You did that last time, so we got information.
I think it's because last time I didn't do this piece correctly.
I think I found it like working through it. I think you didn't, you forgot what piece you had. You added an extra n, or at least you thought, but it actually did belong there from the, one of the steps. And
It happens.
yeah, it just got lost in the math.
And that's going to be your biggest problem, children, in these kinds of situations, is there's a lot of pieces to keep track of. You're going to make some mistakes occasionally. That's why we have solutions to check our work. I will try to post my solutions as well from now on. It may take me towards like the middle of the week for that next assignment. I'll try to post my solutions so you can kind of see my work, and then you can also compare your work to my work to see kind of like what I look for and how I write. They will be in my handwriting. Sorry, I can't replace my hand with somebody else's, but maybe they'll be better. There you go. You said there's also some from 4.3 that were causing you some trouble? I assume along the similar vein with the limits? So the one from 4.3? Nope.
Okay, fine.
Is it alright if I go to that real quick?
Sore. Question? Other homework problems or missing? You've got 10 minutes. You can easily do another time. 57? I can do 57, that's okay. That's your choice. Thrown together by the Beatles. Alright, 57. Use the limit process to find the area of the region between the graph and the function and the x-axis over the given interval. Sketch that region. Y equals negative 4x plus 5. Evaluated from 0 to 1. Okay, to do this, I'm going to use that limit definition we have, which is the limit. It's number 57. The limit as our x, our n, towards infinity of summation I equals 1 to n of f of c sub I times delta x. It's weird because there's two different versions of this, so I have to unfortunately which. I think this is the one from section 4.2. The one from section 4.3, I believe, has delta in it instead. But it's the same function, same works the same way. So as a reminder, these two are kind of really helpful. X sub I is b minus a over n, and c sub I is a plus I delta x. Those two pieces are very helpful for this problem, because if I don't have those two pieces, it's kind of hard to do anything else. So I'm going to start by finding each piece, delta x and c sub I, for this problem. In this case, our delta x would be equal to 1 minus 0 over n. So that'd be 1 over n. That's easy. So what I can do now is anywhere I see a delta x, I can replace it with 1 over n. My c sub I is equal to a plus I over x, I delta x, our a is 0, I delta x. So our c sub I is I over n. Also easy to do. So everywhere I see a c sub I can replace with I over n. So I end up with the following limit. The limit as n approaches infinity, the summation from I equals 1 to n of f of I over n times 1 over n. What I do now, I plug in I over n into my function and start simplifying. My function is limit n approaches infinity, summation from I equals 1 to n. F I sub n just means take I over n and plug it in for x. So negative 4 I over n plus 5 times delta x. So that would be 1 over n. This piece you have to get right before you can continue. So let's go ahead and remind ourselves where it came from. The limit definition is set by our theorem. So there's my limit. I then use the definition of delta x and the definition of c sub I to plug into those two pieces, those two values. Then I evaluate that value, and I'm just simplifying a big limit. Let's do it. All right. I'm going to do some shell work here. The outside is going to always be this piece until I finish. All right. So I have one piece multiplied by 1 over n. I can pull the 1 over n out. That's convenient, at least a little bit. Meaning I end up with this piece on the inside. Now, I can split this into two summations because of the addition sign, which is what I'm going to do. Ready? So, 1 over n. My first summation piece. I equals 1 to n of negative 4 I over n. Summation I equals 1 to n of 5. And again, that 1 over n is being applied to everything. So far, so good? Beautiful. Now, I'm going to pull that negative 4 over n out. I'm going to then simplify each of these two using our theorem. So again, my limit, n approaches infinity, is still the same. My 1 over n is still the same. I want to pull the negative 4 out and the n out, leaving me with a summation from I equals 1 to n of I, plus a summation I equals 1 to n of 5. And now I use my theorems. My theorem states summation of I is n times n plus 1 over 2 plus my other theorem states that the summation of 5 would be 5n, with the 1 over n still out front, still evaluating the limit. Which means I'm now here. Limit as n approaches infinity of 1 over n times this rather nasty looking parentheses. Well, that's all that nasty looking parentheses. Limit n approaches infinity. I begin by distributing the 1 over n to everything. I won't simplify anything until the end, so I have negative 4 n plus 1 over, I have the n from the outside, the n from the inside, and the 2, plus 5n times 1 over n, so it looks like this. Distributing the 1 over the n to each piece. Let's start simplifying. Let's do it. First thing I simplify, I got an n here and n there. That simplifies. Got n's there. That simplifies. I got a 2 and a 4, leaving a 2 on top. I'm left with this. Limit n approaches infinity of negative 2 n plus 1 over n plus 5. These start to look real familiar after a little while because the same ending tends to happen a lot. I take this fraction, I distribute, I simplify, and I split apart. So, I do that all in one step. Limit. And approach to infinity. Negative 2, I'm going to distribute that negative 2 to each piece. And split it into two fractions. Negative 2n minus 2 over n plus 5. So negative 2 gets distributed to both of those. The n splits to both. Leaving with negative 2n over n minus 2 over n plus 5. N's cancel. This piece is 0. I end up with a 5. I end up with negative 2 plus 5. Two problems in a row. The answer's 3. See how that happened. Pretty low help. So these two pieces are critical to our understanding of these problems. We have to really get them right, and then plugging them in and simplifying is just a matter of doing the algebra and remembering that theorem. 4 minutes remaining. If I hurry, I might be able to get through one more problem. One more? If not, Ricky's going to get his homework done. I'm going to step out of the way so you can get both screens.
This one's on 4.3.
Okay. What you got?
Write the limit of the definite interval on an angle where CI is the point uncomfortable. That's it.
Which problem?
Number 9.
No. Yeah. Oh, okay. Yeah. You're going to kick yourself when you see this.
Yeah, I know. That's fine.
The solution is integral from negative 1 to 5. 3x plus 10. Done. Remember, C sub I is our stand-in for x, because remember, C sub I is defined here. And so C sub I is our standard for x anytime we use it. This is number 9, section 4.3. Notice how it takes the function, just replaces all the C sub i's with our x. The delta x becomes dx, and the boundaries stay the same. What you're looking at is this version of it, right here. I should say this version of it. The delta's enough. Questions? Oh my gosh, yes. Thank you. That was probably wrong. dx. Thank you so much. These formulas? They're based upon the same idea we talked about before, splitting the small rectangles and putting them together.
I'm done.
It's just... Okay. So, the limit one? Okay. I'll finish here. This is a fantastic question. What the heck is this main formula? Why does it exist? Who came up with it? Why does it fit there? Newton is this really annoying guy. He's kind of famous in math. I have this feeling that this guy was not exactly polite to his friends. I feel like he was kind of rude. Okay, ready? Here's our formula. Someday. It's going to crash with me. Alright. Let me go back to here. This formula is the integration formula written as a limit instead of as an integral. What I want to remind us is how this A fits into the picture and B fits into the integral. Dang it. If you remind me at the start of class tomorrow, we'll start there. And we'll answer any other questions from section 4.2, 4.3, or 4.4 now. Woo-wee! So excited. And I just can't hide it. I'm about to lose control and I think I like it.
Hey, Gardner and Isabella Ginger to the office, please.